Welcome to our webinar on how to design, build, finance, and operate a food waste digester. I'm Paul Green, and I hold these webinars every month or so in the spirit of education on timely topics in the biogas RNG business. I also run the Biogas Advisory Service. So we have a great cast of speakers today. As you can see here, we'll be talking about leading edge technologies and best practices with some of North America's leading voices on their matter of expertise. I think you'll be impressed by our speakers' level of openness and transparency and their willingness to educate. So today's webinar is sponsored by POC. The POC ThioPOC technology is among the best available for projects where deep desulfurization is required on biogas projects. As the little block flow diagram shows, the ThioPOC unit is a combination of first a caustic scrubber and secondly a biological regeneration system that returns recovered caustic to the scrubber and provides a clean recovered elemental sulfur byproduct. There's a link here to an episode of Biogas TV where we featured a field visit to a very satisfied West Coast ThioPOC customer. You might want to check it out. So today's video is being recorded. The slides from today's presentations will be up on my website, green-tech.com, later today on the events page. You'll get an email tomorrow giving you further information on getting slides or a link to the recording. So today's webinar will be posted at biogas.tv shortly. Biogas TV is where the biogas industry goes to watch a video. I'd encourage all on the call today to subscribe so you don't miss future episodes. So thank you for attending today's webinar. My contact info is here. If we can answer any questions you might have about today's subject matter that we didn't get a chance to get to. So our first speaker today is Brian Paganini. Brian is coming to you today having pre-recorded his presentation over this past weekend. Brian Paganini is the Vice President and Managing Director of Quantum Biopower. He led the design, permitting, and construction of a premier operating large-scale food waste to energy facility on the East Coast. The project is located in Southington, Connecticut, and recycles 40,000 tons a year of food waste, creating 1.2 megawatts of power and 10,000 tons a year of organic compost. Brian leads all facets of the company's operations and business, including the development of new facilities located around the Northeast. Brian also focuses extensively on fostering academic partnerships with the University of Connecticut, as well as promoting new recycling and energy legislation in an effort to create innovation and technology initiatives around recycling in Connecticut.
Hi, my name is Brian Paganini. I am the Vice President and Managing Director of Quantum Biopower in Southington, Connecticut. I'm very sorry I cannot be here with you today. In a proud parenting moment, my daughter is competing for the U.S. Youth Nationals rowing here in Sarasota, Florida. She is, as of today, which is Saturday, the second fastest boat in the United States, competing tomorrow, Sunday, for the finals. So didn't want to let my friend and my buddy Paul down, so I opted to do a recording today. But I am deeply grateful for the opportunity to have this conversation with you all, and for Paul for having these conversations and establishing the platform for these conversations here in the United States, and also a great deal of gratitude for sharing the stage with my colleagues here in the industry. So we're talking about feedstock for anaerobic digesters. And I want to give you a sense of who we are here in the state of Connecticut. We do run a complete organic waste recycling campus here in Southington. Really, it is two companies. The first is Quantum Biopower, which is a legacy anaerobic digester facility that we built here in 2016. It's been operational now for about 8 years, 120 plus customers, recycling roughly 40,000 tons of food scraps on an annual basis. We produce combined heat and power with this system, this facility, and it's one of the longest operating digesters, continuously operating digesters along the East Coast. We're very proud of that fact. Joining us in this campus is Supreme Forest Products, which is a green waste and clean wood waste recycling facility, one of our parent companies. About 7,000 customers on that side of the business, processing 200,000 cubic yards yearly of clean wood waste in the form of stumps, brush, leaves, what have you. So I say this because we've got a lot of experience in treating organic waste, and this is a conversation today around feedstock that is very near and dear to our hearts and very important. Specific to the anaerobic digester, this digester is a two-stage thermophilic wet AD system. It is a high solids and low solids intake, but a low solids operation. As I mentioned, we process 40,000 tons of food scraps. We do have plans on expanding this facility, and we're producing roughly 1.2 megawatts of clean power on an hourly basis, heat along from the CHP system. What's unique to our facility is we do recycle the digestate on the far end of the process. We're turning that into a high-grade compost from the digestate solids, and we'll touch upon that a little bit in some successive slides. I'm coming to you today from a position of a great deal of experience. I think we have one of the most experienced teams in North America when it comes to treating a wide variety of organic waste streams. Again, 10 years of experience on the operations side for the digester, 40 years of experience in the clean wood waste side. So we've amassed this inherent knowledge in our businesses, whether that's transportation of organic waste, grinding and volume reduction, certified product destruction for our large corporate customers, digestion and composting, or debris management services. God forbid, when disaster strikes, we are the team that gets mobilized. We've done this work in hurricane ravaged areas down in the south, Hurricane Katrina, Hurricane Sandy, Winter Storm Pax in the Carolinas. Our team gets mobilized to manage and treat these organic waste streams. So great deal of experience in handling and management, and I think this lends well to this conversation today. When we have a lot of these conversations, right? A lot of folks and groups and financiers come to us and say, what is the feedstock strategy? What does that look like? And we've got the benefit here at Quantum of hindsight being a reality in a lot of cases. The first question that we ask ourselves and we ask other people is, what is your feedstock strategy going to be? Because there's really three drivers that stimulate the feedstock marketplace. It's regulation, policy, and economics. But before you get to those three drivers, you have to ask yourself, do I want to internalize the development and cultivation of the food waste and feedstock for my facility? Am I going to rely on third parties, or is it going to be a hybrid there or both? And the reason why it's important to make this decision early on is everything we talk about here today is under the guise of we want to make sure we are meeting the financial performance and projections we are laying out in our development stage pre-NTP. So when we get into commissioning and commercial operation, we're doing our best to get to those metrics, right? Really, really important. So the first thing is regulation. Unfortunately, in North America, we are a collection of 50 different countries, right? We aren't Italy, we are not Germany, Switzerland, or other areas where on Monday, the government can assign a recycling policy or energy strategy, and by Friday, that is enacted. Very difficult to move the needle in North America because from a feedstock perspective, we do not have a consistent or consolidated recycling policy across the states, right? So relying on regulation is a challenging prospect, right? Even local regulation, state regulation is sometimes tricky. Policies are growing. We know, look at the SEC a couple of months ago. We're starting to look more deeply at scope 1 and 2 emissions tracking, mandatory compliance, and reporting. We do see sustainability policies growing within the Fortune 500 base. We tend to react more specifically to policies versus goals. Unfortunately, there's a big disparity between goals and goal attainment in Fortune 500 businesses that handle a lot of food and food waste. So policies typically get us more excited and drive a lot of our behaviors here at Quantum. We want to see people acting around consistent policies for food waste diversion. And then finally, you have to look at the economics of diverting food waste. If you live in an area or your facility is going to be sited in an area where there's landfilling or energy from waste, you have to look at population saturation and density, whether that's population of businesses, population of people, and then the waste transportation economics, right? What is the cost or the threshold cost of transporting waste from the point of generation to the point of disposal? What is the geographic range? What do those economics look like as far as disposal of transportation of those materials? And how does that factor into your financial projections? In any event, it must incentivize diversion of food, right? We know this. In order to be competitive, we must be lower than the next best disposal option. So this digester that you're planning on, or developing, right, it has to have a value proposition that is a strongly aligned incentive economically and sustainably. Really, really important. Punchline here is that, unfortunately, in the United States, we are very much a waste shed dependent feedstock generation country, and we just believe firmly that the dynamics of the waste shed really drive a lot of those questions. So moving on, why is feedstock so important? We like to talk about project durability. If you are new to the anaerobic digestion operation world, I know many of you on this call are not, and tip of the cap for those who aren't, because we probably have the battle scars to show for, as do we. It's really challenging operating an aerobic digester. I would submit it's many factors more challenging operating than developing and getting a project to notice to proceed. So building a project that is durable post-commissioning should be very, very important, or a high priority in your development stage. And the way that you can ensure better project durability is to spend a proportionate amount of time looking at your feedstock streams as much as you're looking at your kit, your equipment, your technology, and your process thereof for your digester. It's really important. And really what we see when we get projects come across our desk is we don't see that proportionate amount of time being spent on analyzing those feedstock streams. And why is that important? First of all, it impacts design impacts, right? How are you going to treat your food waste streams, depack, remove contaminants, polishing your dilution goals, right? Whether you're going to operate a low solids or a high solids facility, or a hybrid thereof. It impacts your design of your digester, your HRT, your sizing, your material transfer parameters, what kind of pumps you're going to use, diameter piping, biogas polishing strategy, right? Because polishing your biogas is directly related to the constituents of your biogas, which obviously are related to your food waste coming in. It's really important to understand that on a granular level. And then finally, nutrient strategy. What do you intend to do with your digestate stream post-digester? How do you plan on monetizing the value of that digestate? And in a lot of ways, understanding the nutrient makeup of your digestate, which goes back to feedstock, is super critical, super important. Financial fitness of your facilities is obviously important for your creditors, your investors, and your underwriters. Are you confident in your feedstock strategy to achieve, with a high level of certainty, the project projections and the goals that you're setting out for? Because in most cases, particularly with food waste digesters that have a merchant makeup to them, 50 to 60% of the project economics on the revenue side are associated with feedstock, with disposal fees. A less proportionate amount of economics associated with energy production, and then obviously monetizing the value of your digester, your nutrients, is part of that picture as well. But understanding feedstock clearly impacts the bottom line. So, again, financial fitness for facility is super critical when we're looking at the feedstock piece. And then the third leg of it is downtime and operational missteps. The reality is that if you are a developer or a company in the planning or even, I would say, construction phase of a facility, you are most likely making mistakes in your project right now that you don't even know of. Even the best and most highly organized design processes or strategies are making mistakes. And that's not to disparage or to lay claim to inconsistent or folks who aren't doing it right. It's just the nature of our business. We just don't know enough about feedstock in most cases to make really strong and highly competent design decisions. So unfortunately, this puts pressure on the operations team. Most daily facility operational issues, what we've seen in waste to value project, whether that's food waste, MSW, or others, are related to the feeding, fueling, or a feedstock problem, something along those lines. And typically, and unfortunately in the United States, a lot of the facilities that haven't had success, we can point a lot of those issues to feedstock management, feedstock processing, and downstream impacts relative to feedstock. So this just puts kind of a punctuation mark on the fact that the operations is going to suffer when feedstock isn't analyzed in a high level of detail. At Quantum, please forgive the shameless plug. As we're building our feedstock, we tried to build our operations team as well. We do a lot of work with our operations group. We make sure that the culture is embraced very strongly, because when equipment and processes break down, it will be your operations team that suffer those consequences, and it will be the operations group that gets you out of a tricky situation and make sure that the operation of your facility gets back onto even keel. We've experienced this many times. So we subscribe to an honor-based culture here within our company, one where it's selfless action, and knowing that we try to have fun and create a friendly atmosphere within our company. But there's a lot of times, and unfortunately, those times are pretty tricky, where we're spending late nights and weekends managing a certain issue. And it's really the operations team that's going to get you out of those precarious positions when the feedstock strategy didn't think about X, Y, Z problem or issue. We also look at feedstock characterization pretty granularly here at our company. We do develop a feedstock memorandum for new feedstock streams that are coming into our facility. Over time, what we've done is we have a lab operator who will look at type, makeup, contamination, and provide future guidance on new feedstock streams that are coming into our facility, maybe for the first or second time. Over the past 7 years, we've begun to catalog these feedstocks, their type, their makeup, their nutrient density, impact to the facility in the process. And we've built a pretty robust catalog of these streams, which helps our operations team quickly and efficiently assess and assign value to the feedstocks that we see coming into us in any given day or week or month. What we look at when we do feedstock analyses is nutrients, obviously macronutrients and the proportion thereof, fats, proteins, carbohydrates, types of macros, right? Not all macros are created equal. Chemical oxygen demand, or what we like to call the calorific value of our food waste, and the anticipated COD versus the volatile solid ratio, and determining the downstream impacts of that food waste stream into our process, right? The unfortunate part about anaerobic digestion is when we make a decision today, we likely will not see the impact of that decision in the reactor 20 to 30 days from now. And by that time, it's most likely too late. So we spend a lot of time measuring the intended impact of a feedstock very early on to make sure that we're doing our best to our ability to mitigate a downstream impact, which could cause a substantial issue and downtime to the process. Secondly, we look at volume. How much of this material are we going to be taking in? Is it a short or a long-term relationship? What is the volume of that material times the nutrient loading of that material? So we can really assess on a nutrient balance and on a reaction basis what that impact will be. And then the volume of inorganic material. Unfortunately, in a food waste digester, you're going to get contamination, whether that's packaging, knives, forks, things that just end up in a food waste stream. We have to look at what that's going to be so we can assign a proper risk assessment or risk tolerance to that potential impact as well. Percent solids of material, package versus source separate organic material. What is the means and the origination of this material? And again, contamination threshold. And then finally, the commercial relationship. Impact on the client relationship. Is this a new customer, an existing customer? What do we think the commercial terms are going to be? And what do we think the execution risk is going to be? Making sure that when we commit to helping a client or a customer manage their food waste, what do we think the risk of executing on this and recycling this material is, both short and long term? The last thing we want to do is tell one of our customers or clients 6 months from now, thanks, but no thanks. That's just not the way we operate our business here at Quantum. And, we just think that's just good business practice long term. Digging in a little bit more deeply, we have spent a lot of time in our business analyzing food waste labels. We have developed specific algorithms that look at the nutrient balance on food waste labeling, just to really compress that evaluation cycle in looking at different feedstocks. So if we have material coming in that has a nutrition label, we can now scan that nutrition label and assign pretty quickly what we think the impact of this material is going to be coming in from a specific customer. That's really on the packaged food waste side of the business. When we look at source separate organic material coming in, we have a pretty strong understanding on traditional SSO generated streams. However, we do spot checks, and we look at different loads that come in. We'll assign thresholds of meats, proteins, carbohydrates, fats, things of that nature, to make sure that we see consistency in products over time, and also to make sure that we provide feedback back to our customers about what we're seeing in their mix, in their makeup, the material. So they're aware of trends or evolutions in the type of food waste that they're generating. Giving you an example of what we think about when we look at packaged food waste, this is an actual look at when we have a material stream coming in. This is what our lab will generate for us. These food waste streams are sometimes difficult to categorize, but we do our best to look at a variety of different parameters that are very granular in detail, and give our operations group a very good line of sight on what we think the near-term impact is going to be to the facility, and what we also think the downstream impact will be. So again, we're not being surprised by a decision we're making today and how that might impact the facility a month from now. So again, looking at things like total solids, total nitrogen, COD to VS ratio, and COD to total weight ratios are just some of the parameters we're looking at when assigning and assessing value to these feedstocks. The process impacts are something that are outside of the way we classify nutrients. These are kind of the tangible operational impacts. So we will look at ways of identifying potential pitfalls in processing this material. In our facility, we do have a reception pit style receiving facility where we're taking these materials, processing them, sometimes 150, 170 tons per day. So it's really important that when we look at residue rates, contamination thresholds, we're not putting our operations group in a position where they're being set up to fail. We want to make sure that we're giving good feedback, consistent feedback on these materials. So outside of the nutrient makeup of this material and the reaction process, our operations team is not going to get put in a position where this material is going to be difficult to process through the front end of our system. And finally, when we commit to our customers, we're committing really three things. We're committing that we're going to protect their food waste when it comes in. Our process is a guaranteed process, and our people can be trusted. In a lot of cases, the material we're taking in, the food waste we take in, is unsaleable, and because it's unsaleable, we commit to our customers that we're going to handle your food waste as if it is real live inventory. And in doing that, this day and age, it's really important that we are transparently and very confidently projecting a service to our customers that aligns with the goals that they internally have for how they manage their own food inventory. It's really, really important. And finally, at the outset of our digester process, as I mentioned earlier in this presentation, we take our digestate streams and we analyze their nutrient bases and convert those digestate streams into a usable compost, blending them with specific ingredients that are generated on our campus. We use a traditional composting process, and we produce a product called NutriGrow, which is derived from the digestate from our facility, and then gets sold to farmers and growers in the region to really create that circular sustainable model. So really a key benefit to having a really good thought-through strategy on the digestate side, which obviously impacts feedstock because nutrients moving through the digester don't get destroyed, they simply get reformed. And for us, we're just reforming those nutrients into a soil blend at the far end of our facility. So that's it for me. Again, I thank you for your time. I'm very sorry I couldn't be there in person today. Sorry that I can't answer questions. This is my email address. Please, by all means, if there are questions that you have of me at the outset of this conversation, feel free to email me. But in the meantime, I hope you all have a great day. And again, thank you for the opportunity to be here with you today.
All right. That was wonderful to hear from Brian. He's got 8 or 10 years of battle scars there in Southington, Connecticut. So I'm grateful that Brian was able to come. So next up is Mike Muffles, going to talk about pre-processing, digestion, and fertilizer creation with Plant AT Biogas. So Mike has nearly 20 years in the field of agricultural and organic waste management with extensive experience in food waste AD. He was an engineering consultant with a brief stint in government where he focused on nutrient management and land app of organic wastes. Mike has worked on many food waste projects, including managing the owner's engineer team for the City of Toronto's Dufferin Organics processing facility expansion. Of late, Mike has been helping Plant AT to grow into new organics markets, including food waste digestion. So Mike, with that, the floor is yours.
All right, thanks, Paul. I'm going to share my screen here, hopefully get it right. Does that look okay there, Paul?
Yes, perfect.
Okay, excellent. Okay, so I'm going to sort of dovetail nicely into Brian's presentation and dive more into the technology side of after the feedstock is received. So I think Brian did a great job of talking about all of the aspects of securing the feedstock and the project durability. I like that term, the project durability. That's something that we look for. We don't call it that exactly, but something we look for in our design at Plany-T. So I'm going to quickly introduce Plany-T, introduce you to a few project examples that I want to use as a base for describing some feedstock receiving and processing, food waste digestion, biogas composition, and commissioning aspects that I think are somewhat unique to digestion of food waste versus monodigestion of dairy manure or other feedstock. It was Plany-T Biogas. We were founded in 1998. We celebrated 25 years in business last year, over 650 biogas plants delivered to customers in that time worldwide. We've been in North America since 2006 with 3 offices. Our Colorado, Depew, New York, just outside of Buffalo, and then St. Catharines, Ontario. We try to operate and live by our core values of respect, adding value, and climate protection. This is a distribution of our plants and installations worldwide, Canada, US, South America, Asia, and then heavy in Europe, Germany, and France. In North America, we have 33 plants in operation, 14 in progress, 14 additional ones in progress in various stages of design and construction. Of those, 13 in total in North America involve some aspect of food waste. So 3 are standalone industrial or commercial food waste, 80 plants, 10 are farm-based systems that receive some sort of pre-processed or some form of food waste into their operation and into their digesters. And 3 more projects currently in development in various stages of engineering. I did want to take a minute to highlight our construction and service support team. This is a growing part of our business. Our construction support services, if you've worked with Plany-T, there's a construction advisor that comes to site and then helps to ensure that the installation of our equipment goes according to the requirements, our quality requirements, and then they're there to inspect and oversee as that installation is happening. In this photo, the gentleman on the left is inspecting and overseeing the gentleman on the right who's doing, I think, some kind of leak test of the seal on the roof. And so then there are site reports and documentation that we provide to the owner to help ensure that the installation is meeting the installation instructions and design. Our service offering includes digester repair and maintenance, clean out support, RNG, biogas upgrading maintenance. We have a 24/7 hotline that we can put in place for you, and we're getting into operations training and support. I think we've delivered our first few of these sessions to external clients in the last few months. We've started a lab last year, which is quickly expanding. Again, we're getting that critical mass in the US. So the next sort of logical phase of our business is to help support their operations. The training happens through something we call Plany-T Academy. It's something we've been developing in-house for our internal training and staff onboarding the last couple of years, and the plan is then to roll that out externally. We're starting to see that with the external operations training. I think that's mostly been done in person in our Greeley, Colorado training center. I'm not exactly sure when the virtual thing might roll out, but yeah, that's also on the horizon. So what does Plany-T do in terms of food waste plants? So we are a technology supplier, a system integrator. We do process design, and we can do process design and system integration so for all or part of a food waste plant, right? Our core technologies are digesters, our biogas upgraders, but then we can wrap that with sort of the full food waste plant, sort of a part of it, or the full plant as you wish. And some of the project examples that I'll get into will demonstrate that. That's what we do. So we don't own and operate plants. We supply equipment and process design. So just taking a step back and looking at sort of all of these boxes in total make up a food waste plant. And so I'm going to get into sort of some of the technical details of the design. And so looking at, just like Brian was talking about earlier, the understanding the feedstock coming in, understanding your offtake going out, digestion, I think, is critically important, and then what is happening with your gas and your energy offtake. So the first example project it's a confidential client, Midwest US. This project never was built. I don't know if it ever will be. It's in planning limbo. We did the full process design as part of a larger team for the whole organics facility, the pre-processing, the digestion, feedstock receiving, biogas upgrading. Then the nutrient recovery was, that piece was brought by the customer, but that's a design that we went to preliminary design, and then that project was put on hold. Another example project, one of our flagship projects, this has been in operation for over 10 years in Lethbridge, Alberta, Canada. So the feedstock here it's an industrial commercial site with manure that's trucked in, has food waste, fog, potato residues, and was at one point in time processing dead stock, so whole cattle, turning it into paint. But this has been a nice plant operating on a variety of food waste and organic feedstocks for a number of years. We had a minority ownership in that before that was sold as well. So our newest, so this facility is still, this picture makes it look like it's still under construction, but it is actually complete. I should really update this photo. This is this is on farm, what involves manure and food waste, a co-digestion. So it's a food waste plant that happens to be located on farm. This one has a unique consideration in that the nutrients that are imported into this facility have to be exported again, and there's a whole nutrient recovery piece on the back end that I'm not going to get into a lot of detail on, but is very interesting. The last project that forms the basis of what I wanted to talk about is in Ontario, and this is primarily residential SSO plant. It's 140,000 tons, US tons per year of primarily the residential food waste with some capacity for some liquid and solid pre-consumer materials to go in as well. And our scope here is primarily the digesters, some screening, and pasteurization and heat exchangers around that digestion equipment. But we were involved as part of the larger process design for the whole facility. So just as Brian described, feedstock digested in biogas, sort of the inputs and outputs of these things are the key criteria, of course. I'll be focusing on the feedstock piece as part of this. And again, just like Brian described, quantity, quality, and then thinking about the logistics of receipt of that material. So this is how I like to think about the food waste, or this is one way to sort of carve up this pie. So food waste can be thought of as pre-consumer, post-consumer. The pre-consumer can be packaged or unpackaged, and then it could come as solid or liquid. The post-consumer can come on smaller collection trucks and more of them, or larger transfer trailers and less of them. They can be dump trailers, potentially live bottom. The collection trucks will have the main material that they're delivering, but it will also have swill tanks and liquids that have to be received, right? And so thinking about designing a facility from the site layout all the way through the processing equipment and the digesters and what happens downstream starts with understanding sort of what type of material you're bringing in and how it's being delivered. So what is solicited? So instead of using the words contaminant, I like to use solicited versus unsolicited materials. In some jurisdictions, bin liners, you'll have biodegradable bags as bin liners or film plastic bags as bin liners. And often these are not things that you necessarily want in your digester, but they're solicited materials as part of a collection program or permitted materials. So they're materials that you know that you're going to have to deal with on top of the materials that contaminants that are unsolicited. Is it just a food waste digestion plant, or are you co-digesting with other materials, manure, for example, or green waste? Is there going to be variation, seasonal variation in materials or spikes? Is a grocery store that you're receiving from doing a special on cantaloupes one week and you get a roll-off bin of cantaloupes? And how are you going to feed that into your system? So, and then thinking about types of packaging, right? So glass has special consideration, and film plastic tends to get in everywhere and wind around anything that rotates. And a last point here is thinking about recovery. So do you need, as part of your plant, to recover and recycle any of these, the glass or recyclable plastics? That's going to differentiate how you operate your plant and potentially design the pre-processing system to be able to recover those materials. Okay, in terms of site layout, so this is an example from Lethbridge. So this site is sort of a long, narrow site. This site was designed many years before I arrived at Pliny T. But one of the things that you'll note, trucks come in the top left at number 1, and they sort of go around sequentially in the numbers. So they come in, go over the weighbridge at 2, in through a drive-through receiving hall at 3, and then back out around, and then back over the weigh scale at 4, and out of the site at 5. You'll notice this is a sort of a single file, one-way direction going counterclockwise around the site. And this is a nice sort of uniform traffic pattern that minimizes interference and conflicts with truck movements, right? It's efficient. So this is a nice orderly that, fortunately the site permitted this layout. It's not always possible. One of the things that had to be done to permit this kind of truck routing, though, was the drive-through receiving. There was really not a lot of room on this site for facilitating trucks to drive up and then reverse into a receiving hall. So the drive-through receiving was a key to sort of ensuring this truck movement on site. So this is what the drive-through receiving hall looks like. You drive over a hatch in the floor that opens, and then you tip back into the pit, and there's an automated hopper below that to receive the material. So I try not to spend too much time explaining this one. So this is that project in Ontario. So this is a preliminary design concept, so that the site layout has changed since this, but it's enough to sort of explain what I want to explain here. So here there were certain site constraints that did not allow us to do a nice sort of counterclockwise single direction flow. So trucks had to come in and exit out of the one corner of the site. And you can see that there as 5 and 1 here in the top left corner. The weigh scale is behind the building here that you can't see it. So there, I think there's an in and outbound. And then the trucks, as they're coming in, they turn right behind this building and then come out. And they come out right in this bottleneck area here. And there are trucks that in the smaller mechanical building have to go in and out. There's other bays and truck doors, trucks coming in and out, backing in and out. And then the main thoroughfare right in the middle of that. So that of course is a sort of a heavy pinch point that is not ideal. But if you look at, but this was constrained for a number of reasons, right? So we managed to eliminate this pinch point, but not all of the site constraints here. So I'll show you the sort of, even though as the trucks come out and they have this wide area, this big area for maneuvering and shunting and backing into these various doors. So 3B is where the materials go in the receiving hall. And the other doors there to the right are for materials that are leaving the facility and for liquids receiving. So there's truck movements for ways, there's enough room for trucks to get in there, some queuing, turn around, access the doors. There's going to be a lot of conflict and interference as trucks are leaving at the same time as trucks are coming in. So is this ideal? No. Is this this was somewhat unavoidable due to the site constraints. One of the site constraints I didn't mention was that the doors and the main activity of the site had to be shielded from one direction of the property. So the doors all had to, so more or less, were forced to be pointed in this direction, which further sort of complicated things. In the end, the truck traffic was diverted around the tanks to allow for more queuing in that direction, which solved some of the queuing interaction here, but it created other sort of conflicts as well. But anyway, so that's part of the consideration. And this was, if you remember, residential SSO. So a lot of so both transfer trailers and curbside trucks are delivering here, but there are peak times when the curbside trucks are delivering just before lunch and just before the end of the day. So this could get quite busy with those little curbside trucks. So pre-storage tanks. So after we've sort of got the material on site, next is how to temporarily store the material. So just as an example, talk about liquid receiving. So there are 3 pre-storage tanks. 2 of them have to do with liquid receiving. One is the DPAC waste. Actually, one of these tanks is a digestate storage. But you'll notice here that it's packed in nice and tight between the 2 digesters on the right. This 2 rectangles here on the left is the biofilter. Sorry, I'm moving my mouse on my wrong screen. And the concrete building in the back is the process building and receiving hall. So the nice tight location and placement of the tanks allows so a nice valving block to be just inside the process building. All the valves and nice centrally located, short pipe runs, very convenient, easy movement of materials between the tanks. Your photo on the right, you can see the tanks completed, concrete tops on 2 of them and soft tops on 2 of the others. So in terms of the liquid storage considerations, I want to take a step back and first consider the digestion process again, right? So we put organic materials in a tank. We don't want them to digest in the pre-storage. These ones weren't connected to the biogas collection system, but they are going to degrade whether we want them to or not. So if you think about a digestion process, so first step is hydrolysis, and then we get into acidification and acetogenesis, and we're generating gases like H2S, hydrogen, in a matter of days, potentially. And so what we want to try to do when we're thinking about how we design, but also operate these pre-storage tanks, is we want to try to slow down as much as possible that biological degradation. So one of the things, is thinking about what materials we're blending together in these receiving tanks. So if you're blending sort of fresh material with pre-digested material, whether that's manure that's digested in the gut of a cow, or you're recirculating digested processed water, that material are going to have the bacteria and seed and accelerate the start of the digestion process, right? So thinking about what materials to blend together, which materials to store separately, is key to minimizing sort of both the gases and potential odors, the strength of the odors coming off these tanks. So another consideration is how often are the tanks fully drained, right? So every tank, so all these tanks are mixed in some way, shape, or form. But every mixing system has a dead zone. And so there'll be some amount of material that won't be mixed and will be left to essentially be anaerobic. And that will be a growing and breeding ground for methanogenic and other bacteria that are going to promote and accelerate the biogas production. So grid accumulation, right? That's going to create another dead zone. So how often are these tanks drained and cleaned so that material is kept fresh and not allowed to degrade? Keeping temperatures down. So keep doing this, sorry. Will help slow down the biological processes, headspace, air collection, and control, right? So our gas is allowed to accumulate. One of the tanks that I showed you had a peaked roof. So hydrogen lighter than air, that will tend to accumulate in that peak if there's no discharge. those kinds of considerations. So this air, if you're putting it through your odor treatment system, will be highly odorous. If you're going to put it through an odor control system like a biofilter, you'll want to mix that and dilute that with your high volume, low odor concentration building air. And so the ductwork design needs to allow for that proper mixing, right? So you don't want this sort of very wet, heavy air from the top of the tank. It will not mix well with the relatively dry air from the building unless it's given the right kind of baffle or mix design in the ductwork or sufficient length of straight ductwork to allow that mixing. And thinking about what happens when your odor treatment system is offline. So in our design, the ductwork goes through the building, and so contingencies are in place for dealing with what happens if the odor treatment system isn't working and the gases and air in those tanks can't flow through the odor control system. Okay, so this is the concrete building that was behind the receiving tanks. The left third here has to do with the receiving and pre-processing at the facility. The right 2/3 or more has to do with the digestate processing. So this, and I'm not going to get heavy into the digestate processing, but there is a dryer and a pelletizer and mechanical vapor recompression for concentrating liquid nutrients. And that all has to do with the nutrient export strategy for this project at Dicklin's Biogas. And that's a whole other conversation and session, but extremely interesting. So all of the nutrients that are imported onto this farm then are exported as fertilizer. So, but our depacker unit, it's a single depacker unit here. This is about 50% manure, 50% food waste with an automated hopper, trucks back up in the bottom left-hand corner. There's a receiving bay. It was just designed as an open floor so that the operator could decide how that space could be used, whether that's shelving for pallets, whether an additional sort of glass crusher needed to be installed if there were going to be a lot of glass coming in that couldn't be handled by the depacker. And then that material could be fed directly into the receiving hopper. So typical depacker. So we work with a number of depacking companies and suppliers. This one happened to be a Smecon. And yeah, it's an automated hopper with a lid. And yeah, it works fine as you would expect. So no complaints there. So this is what it looks like. Various packaged materials going in and a slurry or pulp coming out. A key consideration is with the pre-processing is grit removal, right? So the depacker is not going to remove everything. Ideally, if possible, you would like some further grit removal. That can range from a hydrocyclone on the left to some kind of gravity settling, either horizontal tank or vertical tank on the right. Generally, hydrocyclone needs lower TS to operate more efficiently, I think 8 to 10%. And the gravity settling can operate at higher, but of course, the higher the TS, the slower the settling is going to be and less effective. So, and of course, for a digester, we want higher, as high as possible, is that the biology can handle organic loading and total solids. So this is a little bit of a balancing act to get grit out without removing too much of the organics that we want to digest. Yeah, so this is really, I think, something that I don't think we have fully figured out as an industry and have a secret sauce. But this hydrocyclone in the system that it's designed for can work really well. Both of these systems end up with a classifier to remove as much of the water from the grit before it's deposited into some kind of roll-off bin or other device to collect it and carry it off. At some point in time, the solids is going to be so high that grit removal isn't going to be effective or make much sense. And it can be a strategy to use assume that you're going to use the digester, that some solids will accumulate in the digester over time, and that you're just going to build into your business plans and operations plans to be able to shut down the digester, drain it, clean it, and then bring it back online. So we think about the digester, and our most of our digesters that we've sold so far are the flat style with side mixers, externally mounted side mixers with a soft top. Part of the strategy that we use is that some solids will accumulate in the digester. So not part of the strategy, but we plan for it and account for it. But the softening, so in the digester, as the organics break down, that material is going to become less viscous, and then we can do a screening on the back end of the digester to remove any impurities that come out. So our clients have had good success with these 2 units, Berger, BioSelect, Huber Strain Press, just 2 examples. There are others out there. So following the digestion process, a final screening before dewatering and nutrient recovery. So like Brian said, design starts with understanding feedstock. And so I think he said it best that, over time, the recipe is going to change. So even from the need of wanting to keep a customer happy, accepting a material that even might not make sense from a tip fee or biogas revenue perspective, but you need to keep a customer happy and take a load or 3 of some material, that's going to change your feedstock recipe over time. So there needs to be robustness or durability in the design. These are some of the numbers that we design around, right? So we try to nail down a feedstock design basis with the customer as a starting point. You have to start somewhere, and we build in some flexibility. So organic loading rates, trying not to exceed too much above 4.5 as a starting assumption. I mean, of course, you can go a little bit higher, but again, leaving some wiggle room. HRT of 30 to 40 days. You can go lower again, but again, leaving a little bit of wiggle room. And this will depend, right? So the more that the feedstock recipe is known and understood, we can tighten this down. But if it's more generic, then a little bit more wiggle room, contingency built into the design. Nitrogen is going to be a limiting factor in the design of a food waste digester. So we're looking at total nitrogen. If as long as it's less than 6 or 6.5 kilograms per metric ton or 13 pounds per ton, that's pretty safe, the total mix going in. When we get close to that or above that, we start to look at free ammoniacal nitrogen. And this is not a measured parameter. This is a calculated parameter that depends on pH and temperature. And then we can try to squeeze a little bit more material that's high in nitrogen, high in protein, for example, in through the digester. TS, so big range. Of course, organic loading, you want to optimize that to the extent possible, higher TS. But if grit removal and digestate quality are of a key concern, then going up to 16% is going to present challenges in that regard. So there's trade-offs here on each of these parameters. And nitrogen often, especially if we're recirculating digestate without removal of the nitrogen or nutrients, can quickly accumulate and start to change the pH and cause inhibition in the digester. So Paul asked me to talk about digester types. I guess we're used to seeing sort of the soft top digesters, pancake digesters, as sometimes they're affectionately called, on dairy or manure or egg projects. And we start to see more of the tall digesters, fixed roof digesters in more industrial applications. Is one better than the other? I don't think so. With respect to feedstock, both food waste can be handled in both equally well. That's fine. There are benefits, of course, for the tall digester. They're higher volume for a given footprint. They're typically 24 meters in diameter by the same height, whereas the pancake digester might be 30 or 34 meters. For a large one, the insulated roof, so that it's all steel construction and can be insulated in all directions. So that's going to have a thermal efficiency benefit. And then for the top mounted mixer, the assumption here, a mixer electrical efficiency can be somewhat better. With the pancake digesters, not all of the mixers, which have larger motors, are running all at the same time. So it's not as sort of different as you might think, but there is still a benefit there. With the shorter squatter pancake digester, I think some benefits are integrated biogas storage on top, right? So in the picture in the top left, you can see actually a two-stage system where they integrate both a fixed roof tall digester and a pancake digester as a secondary. And part of the reason for that is the integrated biogas storage above the secondary digester or digestate storage. So it's a way to elevate it and get it above the ground. The pancake digester has the integrated biological H2S reduction, right, with the netting that goes above the tank. We can get H2S down to below 500 ppm, maybe with some addition of oxygen or ferric chloride or ferrous hydroxide. But that we can have an integrated H2S reduction. Lower static loads in the soil. So if you're in marginal soils, this will have less of a loading on the soil and may overall have a lower cost to construct if your deep foundations don't have to go as deep. So the bottom left picture is a pancake digester being cleaned, a food waste digester being cleaned. Grit accumulation can be significant over time. I think this is after 10 years. So it's not happening every year. In this photo, it can be easier to clean a pancake digester. Not to say that it's not possible to clean a tall digester as well. The panels, of course, can be removed off the side of the tank and put back on. But if the panels are removed, then that has to be tested, liquid tested, everything again. Removing the top of a soft top digester takes days and is quite easy to do. It's a common thing to do. So different horses for different courses. Biogas composition. So I think the two things I want to point out are the H2S is high, maybe not as high as in dairy manure projects, but still high enough that something needs to be done to bring it down. With a hard top digester, a tall digester, that you're looking at probably 2,000-3,000 parts per million of H2S. With the soft top, we can get that down lower, as discussed. The other high element of VOC is with the majority of that being terpenes. And the chart on the right that I found in a report just shows the proportion of food waste in the substrate and sort of, at least in this study, it looks like a clear linear trend, the increase in terpenes with the increase in food waste in the digester. So VOC is something else that will need to be considered as part of the preconditioning ahead of biogas utilization. And I think there's another speaker speaking on that topic coming up, but I'm not going to get into that in much more detail. The last item that I wanted to talk about was commissioning digesters. With manure or wastewater, there's typically a pipe and you open a valve and turn on a pump and all your feedstock is there, hopefully, and on demand when you need it, you can turn it up, turn it down, turn it off, and you have control over your feedstock supply during your commissioning process. With a food waste plant, of course, the food waste is everything is coming essentially and leaving on trucks in a simplified view of things. And so this requires some careful planning. So the first piece is leak testing. So where is the water going to come from and where does it go temporarily if there's a leak? So if you're in an urban area with urban water supply, that's one consideration, versus if you're in a rural area and you don't have a well or you're not connected to a potable water supply, this is a very different proposition. And if you don't have water or not willing, or it doesn't make sense to truck it in to do your leak test, which often it doesn't, you have to think about a contingency. So if we start filling this with, if there's manure involved, great. If there's not, we have to truck in all of our food waste, and we start filling it and there's a leak. What happens if we find a leak partway up? infilling a tank. So in my experience with the projects that I've been involved in, which are sort of my pre-planning T days, doing panel line steel tanks, we've usually always found at least one leak. And so filling with water, draining, fixing the leak, refilling with water, and then hopefully we've caught all the leaks in the first go. So that pumping and moving of water around, of course, takes time, right? So the initial fill can take a week or so, depending on the size of the digester. It's often faster to move materials between tanks if you have multiple tanks. But that, yeah, draining and filling and drying and fixing all of that adds weeks to your commissioning schedule. Where does your seed material come from? Ideally, your seed material is a similar type of digestate with fed a similar type of feedstock as your digester, but that's not always available. So where does that come from? How much of it do you need? Work with your biogas or digestion tank supplier to figure that out and figure out how to start up a digester. But that seed material, which will help, that needs to be organized. And as the seed material, if you're taking digestate from another plant, if there's a process upset at that plant and you don't have access to that material, they can't provide it when you need it, what's your backup plan? And then, of course, feeding the beast. So once you start feeding this, you can't stop. It's not exactly true. Of course, you can stop for short amounts of time. You can slow it down. You can stop for short. But if you stop for too long, of course, that's just going to delay sort of the re-ramp up and getting your commissioning schedule back on track. So thinking about your feedstock supply, working with your suppliers so that they know that your needs are going to be variable. You'll be ramping up over time, but as the commissioning goes, you may run into some trouble and need to stop accepting material for a while and then restart, etc. Whereas the digestate going to go, what if you have to empty a tank unexpectedly, leak testing or other issue, and the tank needs to be drained quickly? Do you have another tank on site that you can move material to? Or if you don't, what is the plan for that? And then also, there are a number of pieces of equipment, right? If you think back to the flow chart that I had earlier in the presentation. So all of these pieces of equipment, and if you add nutrient recovery, all of these systems need to be started up, and then will have their own commissioning and startup challenges. So for example, if your grit removal system, which you're sort of counting on to keep grit out of your digester, goes down during commissioning, do you keep feeding the digester? Do you and wait for the grit removal system issues to be troubleshooted, or do you pause the whole commissioning of the whole plant because of the grit removal system? And what are the implications? And just as an example with the grit removal, but you can go through each piece of equipment and work your way through that. And then lastly, sort of completing a final performance acceptance test. So often you're designing a plant not necessarily for the feedstock that you have today, but the feedstock you hope to have, at least in quantities, a few years from now, right? So you're not fully built out on day one. So can you fill it for the performance test, or will you be doing a test with less than the full design capacity of the plant? And then, yeah, don't forget to put your vermin, pest, and odor controls in place before you start accepting waste, because that they will find it, and the odor issues will happen very quickly once you start taking waste in on a regular basis. Last point for me is, so our systems, CI scores, everybody, I think we're trying to build our systems that are more energy efficient. So our, more heat recovery throughout the system, maybe smaller boilers as a result, which is fine once you bring the system up to temperature and it's running along at steady state. But how do we bring the system up to temperature initially? And thinking about seasonal timing. So if your construction or commissioning schedule has you for bringing in a boiler and your plan is to start it in September or October in Wisconsin, and you're off by a couple of months now. You're starting and trying to heat large tanks of liquid in the middle of winter. And what does that, what are the cost implications to your commissioning and startup? And with that, I think I'm gonna stop there, Paul.
Great. Thanks, Mike. Super job. We appreciate it. So next up, we have IVAS presenting about gas upgrading. So with IVAS is Prabhu Rao. So Prabhu is the executive chairman of IVAS Energy Solutions and president and CEO of IVAS Adsorption. He spent most of his career in the clean energy industry and has led companies in the hydrogen, fuel cell, and biogas industry. In 2023, he, along with a group of investors, including Enbridge, acquired the assets of Xebec Adsorption. He is working to position IVAS Adsorption as a leading product organization in the biogas, hydrogen, and carbon capture markets. He's based in Boston and is pulling for the Celtics to win the NBA Finals. So with that, Prabhu, the floor is yours.
Are you able to hear me, Paul?
Yes, just fine. Yep, you sound great.
Excellent. So, Paul, thank you for that. And Mike, thanks for that excellent presentation. I think there are a few things that you touched on, and I know you and I haven't talked before this, and you talked about H2S and VOCs and the commissioning timeline and the scaling up. And I think these are some of the topics that I wanted to address in my presentation. Thank you for that. I wanted to give maybe a quick overview of the company first, and what we do, and then really get into the biogas upgrading activities for food waste. So IVAS, which is, as Paul mentioned, we have acquired the assets of Xebec, and we are continuing the business. The two core technologies in the company are temperature swing absorption and pressure swing absorption. So TSAs are used mostly for dehydration. The company had started with air dryers as the original technology. I think it was the late 1970s when the company Xebec had started as a company. Since then, it's evolved, and we have done a lot of work in CNG, basically gas dryers for CNG stations, and then it's evolved to dehydration products for mobile pipelines for RNG. So we've deployed a lot of those, and more recently, we've introduced products in the green hydrogen space, which is dehydration of hydrogen coming out of electrolyzers. So that's more on the TSA side. On the PSA side, pressure swing absorption side, we do gas purification. And the novelty that IVAS has is our rotary valve technology. What it basically does is miniaturizes a PSA solution. So a typical IVAS PSA would be about 1/3 the size of a conventional PSA. So on the image there you're looking at, on the right side is the rotary valve. And then the other expertise in the company is basically selecting adsorbents. So think about a PSA like if you were to compare that to a computer, there's the hardware and then the software. The adsorbents are really the software, and the rotary valve and the tanks are like the hardware. So by changing the adsorbents in the beds, we're able to get very different performances. So as an example, this is our 9-bed PSA. You see the green rotary valve in the middle. But by just changing adsorbents in these tanks, we are able to do biogas upgrading, we're able to do hydrogen purification, carbon capture, do a lot of work in helium purification, some amount in argon, and occasionally in the oil and gas purification space. So we have deployed about 450 units worldwide. And just to give you an example on the hydrogen side, where we have done more than 300 projects. Traditionally, we would do a lot in steam methane reforming, basically taking natural gas and making pure hydrogen from it. But over the last, I would say 4 or 5 years, we've done hydrogen from gasification projects, from pyrolysis, ammonia to hydrogen, methanol to hydrogen, chloralkali plants to hydrogen. More recently, we have done projects with fuel cell off gas to hydrogen. And the image that you see in the bottom right here with the tanks with the 3 lines on them, that's a project. It's a 2-stage PSA. It's located at the Port of Long Beach. So this is a project along with Toyota and Fuel Cell Energy, where the off gas from the fuel cell, we purify that. And the pure hydrogen, fuel cell grade hydrogen, is used to fuel the cars and the trucks that have come off the ship from the Toyota factories. So you can see there's a great diversity and applicability of our PSA technology. When it comes to biogas specific, the company has been doing biogas from like the mid 2000s. In 2007 was, I think, one of our first project. Done a lot of work in Europe, about 52 projects there. Some projects in about 29 and growing in North America. We did a lot in landfills, but over the last, I would say, 5 to 7 years, a lot in farm manure digesters and organic waste separated materials. And we've got a lot of experience in different type of applications. And I want to now kind of transition more targeted towards food waste and what the issues are related with that. If you look at gas composition, landfills, farm and food waste, this kind of gives you it's a general range of what you see. Landfills are obviously the most complicated because a lot of stuff goes into landfills, especially with for gas upgrading for landfills, the nitrogen and oxygen are a challenge, and PSAs typically have a leg up in that. So we have done a bunch of projects there. When it comes to farm, this manure digesters, as Mike said, one of the big challenges is H2S. The H2S levels can be pretty high. So if there's anything that can be done within the digester to reduce that, I think that's a good use of investment. But when it comes to food waste, in addition to the H2S, which could be high, I think that one of the biggest challenges is the VOCs. And VOCs and terpenes was mentioned as one of them. Terpenes are obviously a major component, but there are other also, I would say, oxygenated hydrocarbons that could be an issue. So when you're looking at upgrading technologies for your food waste digester projects, I think you have to think about the robustness of your solution to these contaminants. I think that plays a very significant role. So I would say let's dive into that a little bit more. So when you're looking at what possible technologies you could use for upgrading, when it comes to landfills, you have water wash and amine technologies that also come in play, which are usually suited for larger sites. But when it comes to your food waste digester side, when you're looking at about 1,000 SCFM, maximum 1,500 SCFM plants, I think the best solutions, I think the industry is going towards is PSAs and membranes. These are the two technologies that are used. And in terms of process-wise, they're not very dissimilar. You have raw biogas coming in, then you have an H2S removal tower, and if your H2S levels are too high, then you have to think out maybe biological separation. But if your H2S levels are 500 ppm or lower, I think you're really looking at activated carbon towers there. Then to deal with VOCs, you need a biogas blower and moisture removal, and then you have a VOC removal tower. So that's the second stage of removing a preconditioning the gas. And this is typically at low pressure. And then the next step is you compress the biogas that comes out of the VOC towers. Then it gets into the PSA or the membrane solution. So the PSAs and membranes are relatively similar in terms of capabilities. Membranes typically use 2 or 3 stage to get to the high recoveries. And PSAs, you can have a 4-bed PSA or a 6-bed PSA or a 9-bed PSA. And so think of the multiple beds as an equivalent to the stages in a membrane solution. So we have and at some stage, the benefit of adding more beds or more stages, you don't get the return on investment. So we've optimized around 9 beds in the PSA, and from a cost optimization and recovery point of view. So we use a 9-bed PSA in our solution. And at the exit of that is where you have an RNG compressor, either for a mobile pipeline application or for injection into a pipeline. And this is typically at a higher pressure. So if you were comparing these two technologies, the major differences are the PSA systems operate between 8 and 10 bar. There are in other parts of the world, like for example, India is now a big market in biogas. Some companies use VPSA, which is basically atmospheric pressure and drawing a vacuum on that. But the recoveries there are not really good. They're probably high 80s in terms of recovery. So we typically operate 8 to 10 bar. and VC recovery is 98.5, 99%. The membranes will run 12 to 15 bars, and their compressors are generally tend to be a little larger because they recycle to get the high recovery. They recycle the gas. So power consumption up to the exit of the PSA membrane system is probably higher for the membranes, but when it comes to the RNG compressor for a PSA system, the pressure is slightly lower, so you probably have slightly higher power consumption here. In terms of durability, I would say as long as the gas composition is controlled and the contaminants are controlled, both technologies are capable of hitting the nameplate durability. Membranes are supposed to last 7 to 10 years. We typically, on the low end for us, the adsorbents in the PSA are 10 years, and we have customers who run these things for 20 years. So I think durability-wise are pretty good. As I said earlier, and I think this was brought up in the previous presentation, I think the robustness to contaminants is really what is something that's a key factor in deciding your upgrading technology. So let's look at that. Let's look at and just so that you're aware, we have run a number of plants, and I'll show you some pictures. Below 50 ppm VOCs in the feed gas. For the IVIS PSAs, we don't need the VOC removal towers. So that's something that's unique about our PSA in terms of the adsorbent beds that we have. So we are more tolerant to that. Obviously, if the numbers are much higher, we would need to add a VOC removal. So these are examples of some of the projects that we have done related to organic waste processing. The most recent one is in the Greater Montreal area. The project is called CEMEX. It's 1500 SCFM. You see 2 PSAs there. So we managed the entire project and did all the site work there. One of our earlier projects was in Italy, 2018. That plant is still active and running. The top left is the City of Toronto Dufferin facility that was mentioned earlier. We actually operate and service this plant today. This plant actually has a biological scrubber on site. And earlier I'd mentioned we've done, I think, like 30 projects in France, and this is one of the plants there. As you can see, in most of these sites, we don't have a VOC removal because the VOC levels have been managed effectively, and we can just use an H2S tower. So just jumping quickly into now being more specific about what are the things you should look for in upgrading technology and upgrading partner, right? One is when you're looking at choosing between technologies, one is obviously recovery is a key factor. What's the recovery you're going to get from the technology? I would say reliability is another really important factor, and we'll see some numbers associated with that. Robustness is what I call as ability to withstand changes in gas composition is robustness. And in the OpEx cost, there are 2 factors. One is power consumption, and the other one is the media change out in terms of the preconditioning bunk beds. I would say an equally important factor that you should consider when you're picking an upgrading technology or upgrading partner is the capability of the company that you're working with. Do they have enough experience in this space? The ability to service, whether they're providing remote service or provide service on site, how quickly can they respond to your requirements? As we talked earlier, that these projects never go according to plan. So how flexible is the company? Are they able to work with you in terms of schedules and in deployment and being responsive to the commissioning timeframes? Flexibility is one. And the last thing I would say, probably as important as any other item on this list, is culture. I think very critical to have a team that you can work with, because this is a long-term investment that you're making, and you need a partner that can be there for long term with you. So I think these are some of the factors that feed into it. Now let's look at some of the actual numbers behind this, because there's a lot of discussion about recovery in the industry, and I wanted to kind of give some numbers to think about as you make your decisions. So let's look at a plant that's 840 SCFM. What I call is a 3 biostream site, and I'll show you the image of a biostream. The assume $35 MMBTU, recovery of 99%, and an uptime or availability of 97.5%, which means you have about 200 hours a year of service. H2S PPM 20 ppm and VOC is 50. They seem a little low, but that's kind of what we have heard from some developers in terms of their ability to provide to the upgrading sites. 10-year project life. And we looked at the impact of variations in all of this on the ability on your revenue generation at a site. I won't go through all of them, but just a couple of them. So look at this is the impact of recovery. So let's assume your base case is 99% recovery. And if you operate at 98.5 over 10 years, a loss of revenue is about $427,000, about $40,000 a year. So if you're operating at 99.5, you make an additional $40,000 a year. But I think the bigger thing that we found that is that the reliability is probably the more critical factor in all of this. If your base is 97.5% uptime or availability, a 1% change in availability of the plant, which basically is 7 hours per month. If your plant's down for 7 hours a month, you lose about $867,000. And we've seen in many projects where the plants are down for 1 full day, 2 full days a month. And that's a significant impact on your project financials. So I would say, and also, I would say we have seen in project execution, like companies have plans for injecting biogas on a certain date, and then through a lot of issues that were presented by Mike, talked about a lot of challenges that come in through commissioning, these projects are delayed by a month. A 1 month delay in an RNG project of this size is about 0.7 million revenue. So I would say, as you're thinking about technology selection, I think one of the key elements of that is reliability, availability, and project execution. So they have obviously significant impacts on the financial viability of the project. The other thing we looked at was the same project, but looked at the impact of H2S and VOCs, and this is an important factor. What it does, if you have a design criteria for H2S and VOCs and the biogas coming in, obviously we design a plant based on that, an upgrading plant based on that. And if you're off on that for various reasons, because you had to take the feedstock from the customer, it has very significant impacts on the financials of the plant. An ideal case, if it's 50 ppm H2S and 20, and you're designing your plant to spend $200,000 to $300,000 a year for the 10-year life, and suddenly you have 500 ppm of H2S and VOCs coming in, what that does is that it causes you to change the media in these beds much more frequently, and in some cases can increase or reduce your uptime significantly. So it's a double impact on the performance of the project. So I would say deviation from design spec has to be managed very carefully, and I think if there are mechanisms about how you can enable that in the digester, definitely to be looked at. I think again the robustness issue. PSAs tend to have a little bit higher tolerance to these deviations. So we have run our PSAs with 300, 400 ppm H2S for days and with almost minimal impact on recovery and no long-term degradation. So something to consider as you look at your technologies. So I would like to end by talking a little bit about BioStream. The question is, why did we start working on BioStream? And this is something that we started in 2018. Right after we did a few projects, our own construction projects in some of our upgrading facilities. We committed to a certain amount of product cost and a certain amount of installation cost. And what we realized very quickly is that the cost of installation was hard to control for various reasons. And some of the items were our own inefficiencies, and some of it was mainly because there were a lot of other players on the site. You have multiple players on the site. The controls integration for a full site is typically not thought through very accurately. There's testing. There's a lot of surprises when you start testing the unit and doing site commissioning work. Permitting delays. Sometimes you're not in control on the dates when the people who come to give you a permit. Weather obviously plays a role in it. So we came to a conclusion that to be able to scale our presence in the biogas industry, we needed a more modular product and standard product, something that you could build in a factory, test in a factory, and then send it to site. And since it's the same product being commissioned each time, the likelihood of something going wrong is much lower. And the last thing we did was we tried to certify the product using a notified body, and we used Intertech as a partner for that. So our goal is really, we want to make biogas upgrading more like a product that you would buy a backup generator from Cummins or Caterpillar, or you buy a biogas upgrader from IVES. So this is what we came up with. A lot of work went into it, from design for manufacturing, design for service, design for assembly, and the ability to use an extended supply chain to be able to build this both US and in Europe. So this piece of hardware, which is a capacity of about 280 SCFM, and a turn down of 20 to 100%. It comes in three pieces: basically the container, the top skid, and a chiller, and there's a kit, the site installation kit that comes with it. But we are trying to make it easy for the site installer also, so that they're able to achieve their timelines and their budgets in site installation. So this product was initiated in 2018. It's in production right now. We have done about 11 sites. 6 of them are operational. We expect 5 more to be commissioned by the end of this year. There are 19 units in the field. Performance of these units have been very good. The bottom right picture that you're looking at with 3 biostreams, that's exactly the size of an organic waste facility. It's 800 CFM, so easy to install and easy to manage. So our goal is really to be a leader in biogas upgrading for this industry, not just from a technology point of view, but also to be a strong partner for companies who are developing these projects. And with that, I want to thank Paul for giving us the opportunity, and look forward to engaging with all of you.
Great. Thanks, Prabhu. Appreciate that. Great information. So next up, we have a speaker about constructability of projects. We have Mike D'Angelo, and I guess speakers will run a little bit behind on time. Anything we can do to pick up a few minutes here or there would be great. So Mike D'Angelo is the operations manager at Galton's Miami, serving as the manager of their Green Technologies division. Mike has over 35 years in the marine industry, with extensive experience in the mega yacht, military, and commercial maritime business sectors, which you'll hear how that connects into RNG here in a second. Mike loves to call Miami his home. So with that, Mike, the floor is yours.
All right. Thank you, Paul. Am I broadcasting okay here? I'm going to go ahead and share the screen. You can confirm. Everybody see that?
Yes, you're good.
Okay, great. Hey, thank you, Paul, for the introduction and the opportunity to present today's webinar. I'd like to say thank you to all the attendees in today's webinar, along with my fellow presenters. So I've developed this presentation related to balance of plant considerations and how Galton's leverages its experiences and principles to navigate through this process with their clients. So a lot of you are going to ask, who is Galton's? So basically, to provide a little bit of background about Galton's, we were founded in 1940 with its first location in New York, and subsequently around the same time in Norway. Through meeting or exceeding our clients' expectations, we've now grown to over 24 locations in 15 countries with over 1,500 employees. The Galton's brand has been an impeccable reputation in the commercial, maritime, and land-based power generation markets as a total service provider. Some of the services we offer: complete large bore diesel engine services, turnkey technical projects, general fabrication and welding, electrical projects, and in-place machining. Galton's backs up our statement of our commitment to quality by making all locations are completely ISO 9001:2015 certified. We're proud of this coveted achievement, as this is a global standard that is extremely challenging to meet and maintain. We must be constantly improving our organization's practices with the primary goal of consistently meeting or exceeding the client's expectations and requirements. So we have a Green Technologies division, It was created in 2010 by Goldens Worldwide out of the need to assist clients with their green directives. The GGT divisions reside in the Americas, the Netherlands, Dubai, and our Singapore locations. Our mission is to help owners navigate the opportunities to integrate environmental compliance and decarbonization, greenhouse gas reduction in both land-based and maritime applications. We have a solid track record with numerous turnkey technical project completions. So, like what Paul just mentioned, I'm going to give you a couple of maritime examples so you can see the similarities with the complexities of a maritime project versus these land-based RNG projects. There's a lot of similarities. So this very first one that I'm giving you, if you guys can all see it.
You're still on your cover slide.
Okay, I don't know what's going on here. Hold on a second. My screen is freezing.
Page down doesn't get you anywhere.
No, hold on a second.
You want me to share from my screen?
Yeah, if you don't mind doing that. I don't know what's going on with my screen. It's freezing up.
Okay.
Let me stop sharing my screen.
You gave me the PDF, so it won't look quite as good, but
Okay. Okay, I'm giving you back the screen. Sorry about that. So let's go to the very first project examples.
okay. Is my screen showing okay?
Yes, sir. Okay, so here to give you an example of one of our challenging maritime projects, here's an example of a turnkey exhaust system sulfur scrubber project for a cruise ship. Scrubber systems are complex systems that completely remove the sulfur element from the exhaust discharge of marine heavy fuel oils, allowing the vessel to meet or exceed current maritime sulfur emissions requirements. The scrubber dimensions, when fully assembled and the semi-sections welded together, are 7 foot in diameter by 39 feet high. So the first photo on the left shows the bottom module being rigged into the vessel, ready to go down through a very narrow vertical void in the exhaust stack. To very precise rigging techniques. The second center photo shows rigging the third module down the exhaust stack, which again is a very tight fit. It's not much larger than the diameter of the module itself, and we were able to rig that successfully down through multiple levels of the vessel. The third photo is a rendering of both scrubbers in the stack and the stack's ancillary supply and return piping systems that were supplied and installed. Okay, Paul, if you can go to the next slide. Project examples. Yep, thank you. Another example of a challenging maritime project. This is an example of a ballast water treatment system installation for a military cargo vessel that transports U.S. military tanks, armored vehicles, and Osprey aircraft. Our scope was to perform very detailed and thorough 3D scanning inside the vessel spaces, provide concept and detail engineering, supply all the prefabrications, and install the complete piping support package, all mechanical, electrical, and electronic equipment, and assist in commissioning. The piping package on this project was completely fabricated and welded out prior to attendance, as with all our projects, except for 3, 4, maybe 5 pipes that will have a field fit joint to allow us to fine tune. And to give you an idea of the size of this system, the green piping that you see to the left, that's 14-inch diameter piping. So it's quite large piping systems, very complex, moving through some very, very restrictive spaces in the ship. Next slide, please, Paul. Okay, now here is one of our RNG projects. So here's an example of a balance of plant RNG installation of an IVUS 2.0 biostream performed by Goldens. We had the full prefabrications and mechanical scope on this site with the installation services performed by our partner provider. The first photo on the left shows the interconnections to the upgrader module, including the HVAC system. The second center photo shows the completed installation of the top skid on the roof of the upgrader module. And the third photo is an overall view of the site prior to the insulation being installed. Okay, next slide, please. Okay, so and here are some examples of another RNG site that we completed. These are examples of a 2.0 and a 3.0 biostream installation in varying stages of development. The first photo on the left shows a 3.0 biostream completed piping package. And as per previous slides, all were prefabricated in our workshop by ASME certified welders with 4 selected areas as field adjustments and welded in the field. The heat trace cabling has been installed and the piping was ready for installation. The second photo shows our mechanical analyzer tubing installation in progress. The plastic tie wraps are only there as placeholders until we firm up the entire tubing installation and layout, then everything is properly and professionally secured to the piping system. Third photo on the right shows the completed positioning and installation of the H2S scrubbers ladder assembly, filter, and associated piping and valves for a 2.0 biostream. Cable trays are shown installed in that area, and heat trace cabling is installed on the vertical scrubber wide pipe assembly. Okay, next slide, please. Okay, now here, Paul, this is a video. I don't know if you're going to be allowed to hit play on that if you hover below the picture. No. All right, we're going to have to pass. Well, there's a video there that I've uploaded this whole slideshow.
Right.
So
We'll have it uploaded to the website tonight.
yeah, thank you. So this is a completed ZEBIC at the time of installation, which is now IVUS, as Prabhu had mentioned, 3.0 biostream installation. The video will show all mechanical, electrical scopes of work completed. Among some of the tasks required, we positioned and installed all equipment, installed HDPE and 316 stainless steel mechanical tubing runs, installed all piping and valves, HVAC system, and insulation. And we relied on our electrical partner at the time to complete the electrical on this site. Okay, next slide, please. Okay, what we bring to the table. Okay, we are self-performing field installers using our own workforce. We have an extensive and broad depth to our team. We have certified welders, engineers, project managers, mechanical and electrical teams. Our services complement equipment manufacturers because we fulfill the request by the equipment manufacturers' clients to provide balance of plant requests. And we lean our experience with countless projects in the maritime sector where there is zero margin for errors or omissions. The safety and lives of the client's crew is dependent on us performing our installs properly. We bring to the table a mission-critical mindset on all our projects. The project must be precise, on time, on budget, and completed to all the requirements. It's critical when choosing an installer that in addition to these requirements, that they have the experience and the depth to perform installations of this caliber. Next slide, please. So proposals, information needed for a proposal development. So we're looking for a full scope of work document, itemizing which requirements are the installers versus the others supply and or install. Engineering package, whether it's FEL1, FEL2, etc. The FEL level drives the type of proposal and impacts the accuracy. Some of the information required depending on FEL level, such as site layout, lifting plan drawings, equipment cut sheets, prefabrication drawings, P&IDs, electrical SLDs, termination drawings, MTOs, and installation specifications. We also like to know if there's any special requirements for the project, weld certifications, NDT requirements, whether the project is PWA or ITC compliant, where are the hazardous zones, is there a hazardous zone plan for where we're working, and site securing requirements. So the more information we receive, the more accurate the proposal. Okay. Next slide, please. Proposal types. Okay. So the proposal types that we like to work with, we like to offer clients is we do what we call T&M, time and material, or as many know is an open book, rough order of magnitude or ROM, a budgetary estimate, which is FEL3 with 60 to 90% of the design completed. And then there's a comprehensive estimate, which is an FL3 100% design completion. So open book is a proposal in which we provide our daily labor rate per trade with an estimate of team size, number of persons with each trade, all materials, travel and lodging, etc. at cost plus. ROM is a broad stroke FEL 1 or 2 proposal in which only the basic information or deliverables can be provided. We can also utilize an engineering project from a similar site as a template to do a ROM proposal. The pricing can swing significantly depending on the accuracy of the final information provided versus the initial information. The accuracy can swing from 50% on the low side to 100% on the high side. Budgetary estimate is a more accurate FEL3 proposal than a ROM, requiring at least 60% of the engineering completed, up to 90%. The accuracy is predicated on the amount of the engineering deliverables that are provided. Accuracy can be 10% on the low side to 30% on the high side, varying depending on the percentage of engineering completion. Then the comprehensive estimate is an FEL3 level requiring 100% of the design deliverables. Accuracy is plus or minus 10%. Next slide, please. All right, PWA ITC considerations. So this program, as most people in this webinar will know, provides significant savings for the project owner. For example, some of the compliance requirements are the installer must comply with prevailing wage and apprenticeship requirements for the state and county in which the project is being installed, with 15% of the labor coming from a registered apprenticeship program. The installer cannot use foreign labor or any labor that is not a green card holder. All structural steel must be 40% domestic content. Non-structural, such as piping and fittings, are excluded from this requirement. As most people will know, these requirements drive up the cost of the project significantly, and the client must weigh these impacts from all contractors to determine if the juice is worth the squeeze. And the PWA ITC full compliance requirement can be challenging for non-union companies. Okay, next slide, please. Project kickoff. Okay. Upon award of the contract, the client can expect a project kickoff to commence, with the client continuously involved. Some, but not all, of the requirements will be: perform a proper and thorough planning phase, comprehensive reviews with the client of drawings, documentation, and information along with our plan, discuss any potential challenges that may arise and how collectively they will be addressed if they arise. Communication, communication, communication. I say that 3 times because that is paramount in our world. Effective communication for us is the only way to get something done and done properly. We like to perform a site visit of a previous install if available. We like to establish an accurate Gantt chart with milestones, subtasks, etc. And we will assign a project engineer who will be on site for the duration, performing project management duties and technical support. Next slide, please. What the client can expect.
We gotta wrap it up, Mike.
All right. I got one more slide.
Yeah.
All right. What the client can expect: weekly meetings and regular GAN updates, daily progress reports, discussion with client of any changes that need to be made from the engineering plans, change orders as needed, professionalism, cooperation, and excellence always. Dedicated and focused team members. Okay, we work 12 hours a day, 7 days a week until the project is completed. And a continuous commitment to quality, no cutting corners. All right, that's the last slide. Thank you, everybody.
Thank you, sir.
All right.
Appreciate it, Mike.
All right.
All right, so I'm going to talk about nutrient recovery and water cleaning here. So Vipin Lilani is going to speak with us from Digested Organics, and Vipin is a skilled wastewater treatment professional with over 18 years of experience in applications engineering, process engineering, and product management. Key expertise in filtration systems, membrane bioreactors, and aeration systems for municipal and industrial clients. So good to see you, Vipin. Thanks for joining us, and the floor is yours.
Yeah, thank you, Paul, for the introduction. So respecting everybody's time, let's get right into this. So I'll be talking about the nutrient recovery and water treatment solutions in food waste digestate. A brief agenda of the topics that we'll be covering today. Talk about our company, Digested Organics, what it does, And then we talk about why is it necessary to treat food waste digestate? What are the benefits? And we'll talk about the various treatment solutions that are available. A follow-up with a case study, how Digested Organics went about designing a solution for the client, and then wrap up with a couple of fertilizers that has been produced as a byproduct. So Digested Organics was founded a decade ago with a vision where all liquid waste are converted to clean water and value-added products. It was founded in Michigan and acquired by Mott Corporation last year in February. Mott Corporation has a total of thousands of commercial large-scale filter installations all across the US and Canada. Digested Organics specializes in the engineering and manufacturing of filtration systems with dedicated project management team to deliver holistic solutions to our customers. We have a team of field service and operations technicians who run and maintain filtration systems all across the US. And let's look at some of the key challenges that we see in food waste digestate. And I know Mike and Paul, they have already touched on this, but the biggest challenge that we see in food waste digestate is the feedstock variability. There are seasonality variants in the feedstock. The nutrients in winter could be way different than what the nutrients are in the summer. The high protein content or high ammonia content or high fiber content will lead you to design differently for these applications. The nitrogen, phosphorus, BOD, COD limits that are posed on the discharge can change your design conditions. Disposal costs could vary due to proximity to urban centers. And feedstocks are often contaminated with plastics due to packaging and often must be dealt with before sending to the digesters. Now, why is digested treatment necessary? So let's look into what are the benefits. When we're looking at benefits, I like to take it as a three-pronged approach of financial, environmental, and social aspects. Now, when we are treating the digestate, you're reducing the amount of liquid that is there in the digestate. So you're overall reducing your hauling cost, thereby reducing your disposal cost. As a byproduct of the treatment scheme, you can get a fertilizer, which can be sold, and that can provide you a separate revenue stream. Through nutrient credit trading, farmers who install nutrient removal solutions could generate nutrient reduction credits. And these credits could then be sold to municipal or industrial facilities like wastewater treatment plants. Also, with digested treatment, you're able to reduce the volatile solids and thereby improving your carbon intensity score. Now, looking at from the environmental perspective, because this waste is sent to a digester and not a lagoon storage, you're minimizing your ammonia and methane emissions into the atmosphere. Digested treatment also reduces excess nutrient runoff associated with dilute digested application. And along with that, it also enables more targeted delivery of nutrients, increasing crop uptake and yields. Now, looking at from the social and environmental standpoint, because you're reducing the amount of liquid in this digestate, you're also reducing the number of trucks by more than 80% on the roads, and also reducing the diesel usages, thereby helping the environment. Now, this waste, since it's run through a digester, you're minimizing the amount of odors because it's not been sent to a lagoon storage or it's spread across the fields. Now, all this nutrient credits that we talked about, as well as the fertilizers that can be produced as a byproduct, it allows to create circular economy for the nutrients. And Digested Organics has developed unique platforms that convert food digestate into resources such as clean water for process, as well as organic fertilizers for crops, thereby producing multiple revenue streams. Now, the way we do that is we have very large number of filtration solutions from primary solids removal and screenings, which remove your largest solids, grit, remove contaminants that could foul the membranes. Following that, you have microfiltration systems, ultrafiltration systems, and superfiltration systems, which can remove your suspended solids. Liquid from these filtration systems can be sent to a reverse osmosis system, which will remove your dissolved solids. Now, finally, you can polish the water coming off the RO systems by using a polishing RO, nitrification system, an aeration system, or a UV system, so that you can meet your discharge limits. The concentrate coming from the RO system can be sent to thermal concentration, such as evaporation or distillation, to achieve zero liquid discharge, and also make organic fertilizers. Now, Digested Organics has positioned to deal with all these challenges and have the tools in the toolbox. But how do we know which ones to use? So the way DO does that is we perform small-scale lab testing to demonstrate filtration feasibility and generate quick design concepts. These are like proof of concepts, and they help Digested Organics to make decisions whether we want to go ahead with the project or not based on the filtration feasibility testing. Now, these sample sizes are small, so they're really easy to run. And we can get quick results of fluxes and chemical dosing requirements based on all the unit operations that we have available in our lab in Michigan. Now, once we've done our lab testing, what Digested Organic does is we perform pilot testing. This is in order to demonstrate influent variability handling and long-term operations. The key drivers for pilot testing are long-term filtration performance, including cycle times, different pressures, chem dosing requirements, cleaning frequencies, also programming updates that can be done. Now, what are the final results of doing the pilot testing? We get a design that is based on actual on-site data and not just engineering guesses. And we also get real cost estimates based on actual tested systems so that we avoid any post-project cost surprises. Looking at a case study, one of the largest food waste to renewable natural gas projects in the US has contracted with Digested Organics for their digested treatment. They are diverting about 200,000 tons per year of waste from the landfills and sending it to the digesters. The project need was to treat 200,000 gallons per day of food waste digestate and produce clean water and additional nutrients. The technologies deployed at this site are automatic screens, superfiltration, RO systems, and ammonia stripper for the filtration system. And then for the solids removal, we have rotary dryers, coolers, heat exchangers, and wet scrubbers. Now, the benefit that the client will achieve with this treatment scheme is a huge volume reduction in the digestate hauling, as well as lower trucking cost and land application cost. They'll be able to minimize the odor because they're sending it to the digested and then through the advanced treatment solutions. On top of that, they will also receive some fertilizer in terms of a concentrated ammonia fertilizer and granular fertilizers. Now, looking at the process flow diagram, so there are multiple digesters on the site, which will be producing biogas, which is a renewable natural gas. The digestate coming from the digester will be sent to a centrifuge. The centrate coming off the centrifuge will be sent to automated screens. These are 25 micron wedge wire screens followed by 25 micron mesh screens. So these are completely automated purging system. From the screens, after the removal of all the grit and solids, it will be sent to Zwitterco superfilters. These superfilters have 1 nanometer pore size and removes 99% of the molecules which are greater than 1000 Dalton. These superfilters handles over 50,000 ppm of fats, oils, and grease. They're chlorine tolerant, fouling resistant, and hence they require less cleaning and less chemicals. Following the superfilter, the clean water will be sent to sub-induction time RO, which prevents silica and mineral scaling. During repeat batch process, membranes experience highly concentrated wastewater for only a brief moment at the end of each batch process. This amount of time is less than the induction time required for typical foulants like silica or mineral scaling to form crystals and scale the membranes. The batch process maximizes water recovery, which can be up to 90%. Since the pressure in the RO starts low and increases during the batch as the material becomes more concentrated, the overall energy consumed is drastically reduced compared to a typical RO system. The concentrate from the RO is sent to a distillation column where then you can produce the concentrated ammonia fertilizer. The cake coming off the centrifuge is sent to a rotary dryer. This cake is about 25% dry solids with 75% moisture in it, and it's reduced down to 10% moisture level. So the cake is then sent to a cooler, then through a screening system, and then to a storage silo so that they can be sent out and sold as a fertilizer. Now, TerraFlow are commercially available fertilizers produced from the waste digestate. The one on the right is the concentrated ammonia solution. These have a little bit higher pH of 12 to 13, so they are volatile, so they must be incorporated into the soil quite rapidly. The one on the right is the concentrated digestate. This is produced at 50% TS levels through evaporation. And even though the concentration is pretty high in this fertilizer, they won't clog the drip systems or the nozzles. And the pH is pretty stabilized at 5 to 6 levels. These fertilizers are OMRI listed with the Organic Materials Review Institute. Thank you for listening in, and I'll be available for any further questions.
Thank you, Vipin. We appreciate that. Thanks for the good work you're doing. So with that, we've got one more presentation to go. I'm grateful for everybody that's stuck it out to the end, and sorry we're a little bit past time, but we're going to get some time with Steve Compton here now, who's the president at Savanna Bioenergy. Savanna is a developer and owner-operator of carbon-negative renewable natural gas projects. As president, Steve manages the company's operations and fundraising efforts. He's raised over $250 million in project finance and development capital over the past 4 years. Before joining Savanna in 2018, Steve worked in corporate ventures on biofuels and carbon investments at Chevron and led the organization in negotiations for several $1 billion of renewable fuel agreements. He's got a BS and MS in engineering from Stanford and an MBA in finance from Duke. So Steve, welcome. Floor is yours.
Thank you, Paul. Okay, so I'll just try to go a little bit about Savanna Bioenergy. We've been working since 2017 to develop and operate over $350 million of RNG projects. We have a very deep team in technical design and engineering capabilities. We finance and project manage the projects we develop, and as well, we operate the food waste digesters and other digesters that we oversee. Our mission is to be a market leader in accelerating the production of RNG derived from anaerobic digestion. And we are currently deploying $250 million of capital into projects in this industry. So be interested in touching base with anyone afterwards on projects you're looking to finance. And just flipping through quickly, a few of the operational references we have among our team members is a facility in Charlotte, North Carolina. It was an electricity generating site, and our director of operations, Jeff, managed this facility for a period of time. We have another facility in the LA area that was developed by one of our team members. And we're actually looking at another facility in the LA area. Currently would become a new project in Savanna's portfolio. So the types of facilities we look for in terms of making investments, and I think this is generalizable across the industry, are a sustainable revenue supply that comes from food waste tipping fees and offtake of the natural gas that's produced. And those could be either fixed price or RIN and LCFS index priced. We limit our investments to proven technologies, and we have several European team members that have built up a very strong experience base, similar to some of the presenters earlier today. Very important to get the technology right in these applications. There's a close match between the performance of the technology you select and your ultimate revenue and investment success. We look for scalable opportunities between $30 and $100 million in a single investment. We prefer a majority investment position, but are open to partnerships. And we both internally develop our projects or we're open to acquisitions. And in terms of investment criteria, we are looking for sort of a 13 to 20% IRR. Those are risk-adjusted returns, and we can put debt leverage onto projects to get a higher equity return. As far as financing these projects, some of the keys are having long-term fixed price contracts, so feedstock, the term, and having sufficient quantity volumes to support the project are critical, as well as a counterparty that is financially stable and has a proven track record in your region. Just skipping down to the RNG offtakes, we do balance every time we make a investment decision between either a fixed price feedstock, RNG offtake, which often is into a voluntary market, like to a utility or a corporate purchaser, against selling the gas into LCFS and RIN type market. And the relative attractiveness of those two options varies depending on specifics of your project and when the project comes online. And then just to mention, digestate treatment, which was just covered, is very important. It creates a revenue source potentially to the project, as well as mitigates what could be a substantial OpEx cost. So we do try to optimize those ancillary products as well. Just briefly touching on debt options for food waste and other waste feedstocks, there's an opportunity to use a tax-exempt bond, which can be a lower cost of capital than a typical commercial loan. They do add additional risks and requirements to your financing. So we are often able and do recommend to consider equity financing through construction, if practical, and use your debt after the project started up and de-risked further. Going fast here, just in the interest of time, and these topics were covered, but the ITC, the current framework expires at the end of the year. But if you start construction and are able to document that through either continuous physical work or spending 5% of the total project cost as a safe harbor, you can grandfather your project into the ITC credit. If you sell the project to a unrelated third party, you can further step up the cost basis, the size of the credit you get. And if you're in an energy community designated by IRS or use domestic content, you can also get a 10% additional credit for both of those. And then to monetize the tax credit and use as part of your financing sources, you can go to the third-party market through a broker or directly take out tax credit insurance and sell it. Or if you have a balance sheet that has taxable income that can be shielded, you can take advantage of it yourself. And this is driving quite a bit of project activity acquisitions over the next 6 months. That's likely to continue. And then looking ahead to next year and through 2027, there's a production tax credit. It's worth roughly $7 per MMBtu of gas produced. And that would compare to roughly a $20 kind of base offtake if you're selling into the voluntary market. So it's a substantial uplift. It requires the use of prevailing wage and apprenticeship for projects that were not started up before 2023. So there's some extra requirements that come with it, but the revenue certainly is attractive and something that we see operators and financiers of these projects planning for. So if you're selling into a non-transportation fuel market, it may not be as important. So that would be a caveat. And then I'm getting close to the end here and just transitioning from finance to operations. So food waste digesters, because there's often a fairly labor intensive and continuous stream of feedstock receiving, it requires either a decision between a daytime only staffing model or even extended hours or 24/7 coverage that can require a lot of personnel. We recommend and usually implement some amount of centralized and remote monitoring of the facility just to manage and make sure that there's a second set of supporting personnel, making sure things are on track and catching anything that the on-site team may be too involved in kind of day-to-day to pick up on. And you'll see in the typical positions, we do have a kind of a management team. You see in purple at the top of our org chart, and we recommend having a environmental health safety manager and looking also to have lab personnel, either internal or contracted, to support managing a food waste digester. That's very critical to keep close tabs on the health and the variations in the feedstock coming in the door. And maintenance and operations are very closely intertwined, but typically you'll have specialists in either. And so we would split the kind of team into an operations focused group and a maintenance focused group. And the maintenance team will need to implement a CMMS, computer maintenance management software. There are a number of very easy to kind of pick up and roll out options. It is time intensive to set it up the first time, but once it's up and running, it certainly makes everyone's kind of lives easier, as it can track regular work order creation, spare parts inventory, manage preventative maintenance. So you're catching and repairing things and doing regular rounds before they occur, problems occur. And then you can also use that data to, from an asset management standpoint, identify causes of failure and fix those, or places where through debottlenecks, small capital projects, you can get more output from your facility. And then safety is something that is critical in these projects. And so that HES person would manage and oversee a whole alphabet soup of regulatory requirements, depending on the size and the nature of your facility, whether it's electricity or natural gas producing. And there's some also new rules coming. The BRR, see the missing R here, if you're generating RINs, will require some additional new gas chromatograph and flow meter certification. Some specific equipment is required. So that's something to be aware of. That's taking effect actually the first round in July and the second round at the end of the year. So if you haven't heard about that, make sure you're implementing it. And then just to round out kind of what it takes to operate a facility, it really takes kind of active management to monitor the uptime, the production, focus on your key performance indicators, and looking at the SCADA, the data system at the facility. There are usually a lot of interrelated causes between why and reason behind why you might not be getting full output. So it's a very, I guess, important role to have in your operations team is kind of that review, analysis, and action, so that you can increase your uptime and output accordingly. And with that, just wrap up there. Thanks for everyone who stuck around. Feel free to reach out to us later. Thanks.
Thank you, Steve. Appreciate it. Okay, well, that does it for us. So sorry we went a little bit over. Hopefully you enjoyed the presentation today. You'll get an email from me tomorrow with thoughts on downloading presentations, and the whole video was recorded. It'll be up on Biogas TV shortly. So with that, thanks again, and we are a wrap.